In the last video, pinag-usapan natin ang first law of thermodynamics for open systems at na-derive din natin ang energy and mass balance equations for the steady-state steady flow or SSSF systems. Sinabi din natin na kapag meron tayong SSSF systems, the rate of change of energy and the rate of change of mass inside the control volume are just equal to 0. This is manifested by these sides of the equations. In this video, pag-uusapan natin ng mas malalim ang iba't ibang halimbawa ng steady-state steady flow systems. By the end of this lecture, you should be able to cite some examples of the steady-state steady flow devices and understand their operation. Malalaman nyo rin kung paano i-derive ang governing equation ng bawat steady-state steady flow devices mula sa ating energy and mass balance equations. Just a recap, sa madaling salita, isa sa mga katangian ng steady-state steady flow systems ay kung ano ang mass na pumapasok ay lumalabas lang din. Walang mass accumulation sa loob ng device at ang net rate of change in energy ay 0. Ilan lang sa mga halimbawa ng steady-state steady flow devices ay ang nozzles and diffusers, turbines, heat exchangers, at throttling devices. Let's go through each of them and derive their governing equations based on certain assumptions that we can make. Unahin na natin ang nozzles and diffusers. Ang pinaka-goal ng nozzles and diffusers ay baguhin ang fluid velocity by changing the cross-sectional area of the flow. As a further consequence of this, the fluid pressure across the nozzles and diffusers also changes. If the device increases the velocity of fluid in the direction of the flow, then it is called a nozzle. Makikita ninyo ang mga nozzle sa mga garden hose kapag nagdidilig tayo ng mga halaman. Mula sa high-pressure, low-velocity fluid sa loob ng hose, the change from a larger cross-sectional area to a smaller one during a subsonic flow produces a high-velocity, low-pressure fluid. On the other hand, if the device decreases the velocity in the direction of flow, then the device is called a diffuser. Now, let's derive the governing equation for nozzles and diffusers. Una sa lahat, ang nozzles and diffusers ay hindi nangangailangan ng power input at hindi rin naman sila nagpo-produce ng power output. Therefore, W.CV will then be equal to 0. We can also assume na walang heat transfer ang nozzles and diffusers with the surroundings. So, pwede nating i-drop na lang ang Q dot from our equation. Madalas din na sila ay may single stream of mass flow, which is why we can omit the sigma notation in our energy equation. Not only this, but M.I and M.E are equal to each other. That is according to our mass balance equation. So we can divide both sides of the equation by these masses, cancelling each other out. Unless otherwise specified, maaari nating i-neglect ang effect ng elevation between the mass inflow and the mass outflow, which is why the potential energy components will also cancel out. In the end, we have this governing equation for nozzles and diffusers. Next, we have turbines. Turbines are power-producing devices. Ibig sabihin, ang primary purpose niya ay makapagbigay ng power output, usually in the form of electricity. Mula sa high-temperature, high-pressure fluid sa turbine inlet, energy is harnessed as the fluid passes through a set of blades connected to a rotating generator shaft. As a consequence of this, magiging mababa na ang energy content ng ating working fluid at the turbine outlet. This is manifested by its decreased temperature and pressure. Now let's derive the energy equation for turbines. Unless otherwise specified, pwede nating i-neglect ang effect ng change in elevation between the inlet and the outlet of the turbine, which is why the potential energy components may be neglected. Especially in our steam turbines, kadalasang maliit lang ang energy contribution ng fluid velocity compared sa mga enthalpies na makikita natin sa thermodynamic tables, which is why the kinetic energy components may also be neglected unless otherwise specified. Finally, kung meron tayong adiabatic turbine, ang heat transfer nito with the surroundings ay equal lang sa 0. Therefore, Q dot will vanish. In the end, The power produced by the steam turbine is equal to the summation of the rate of enthalpy in minus the summation of the rate of enthalpy out. Next, we have compressors and pumps. Ang pinaka-purpose ng compressor at pump ay mag-increase ng pressure or elevation ng ating fluid at the expense of power input, usually in the form of electricity. Now, what is the difference between the two? Kapag ang ating working fluid ay gaseous or vapor substances, tulad na lang ng steam at air, then we use a compressor. Kapag naman ang ating working fluid ay liquid, then we use a pump. Ang mga assumption natin for the compressors and pumps ay parehas lang sa mga assumption natin sa turbines, which is why we have the same equation. So next, we have heat exchangers. The purpose of heat exchangers is to transfer heat between two working fluids. So marami tayong types ng heat exchangers, and they are classified based on the direction of flow, on the components involved, and on the manner of heat exchange. But mainly, they can be classified as direct contact or indirect contact heat exchanger. Kapag sinabi nating direct contact, ang mga working fluid ay naghahalo sa isang mixing chamber kung saan nagkakaroon ng heat exchange. Kapag naman sinabi nating indirect contact, walang mixing na nangyayari dahil sila ay usually separated ng metallic tubes or pipes. Now, let's derive the energy equation for heat exchangers. If the heat exchanger has a heat transfer efficiency of 100%, masasabi nating wala itong heat transfer with the surroundings, which is why Q dot is equal to 0. Also, ang heat exchangers ay hindi work-producing or work-extracting device, kaya naman ang value ng W dot CV ay 0 din. We can also neglect the effects of the velocity and the elevation of the streams of masses unless otherwise specified. Kaya naman pwede nating tanggalin ang contribution ng kinetic and potential energies. Therefore, the governing equation for heat exchangers is as follows. Ang pinakahuling steady flow device na pag-uusapan natin sa videong ito ay tinatawag na throttling devices. So when we say throttling devices, ang pinaka-purpose niya ay mag-reduce ng pressure without extracting useful work. How can this be achieved? It can be achieved by introducing a restriction along the line where the fluid flows. Ang pinakasimpleng halimbawa ng mga throttling device ay yung mga gripo sa mga tubo sa ating bahay. We can actually modify the pressure before and after the throttling valve by twisting these valves. So, in the process of decreasing the pressure, also, nire-regulate din natin yung mass flow ng ating tubig. So, that's how throttling devices work. Now, let's derive the energy equation for throttling devices. Sa ating flow, meron lang tayong isang stream of mass flowing in and out of the throttling device, so we can actually omit the sigma notation here. We can also assume na walang heat transfer with the environment, so Q dot will just be equal to 0. Nasabi din natin kanina na ang throttling device ay hindi work-producing or work-receiving device. So, automatically, W.CV will vanish. We can also neglect the effects of velocity and elevation of the streams of masses. Kaya naman, pwede nating tanggalin ang contribution ng kinetic at potential energies. Finally, we have this very simple energy equation for throttling devices. Take note na sa lahat ng steady flow devices na ating diniscuss ay applicable ang ating mass balance equation. So, especially in the cases na maraming streams of mass flow, definitely kakailangan din natin yung mass balance equation para mag-solve ng iba't ibang thermodynamic problems. Also, I understand na marami tayong diniscuss na devices sa videong ito. So, makakatulong siguro na gumawa kayo ng summary ng lahat ng mga equations kasama na rin yung iba't ibang assumptions. So, I would recommend that you familiarize and if you can memorize the assumptions, it will be really helpful. Before we end this video, let us solve a sample problem about steady-state, steady-flow devices. Let me just read this problem for you. A small turbine is operated at part load by throttling a 0.25 kg per second steam supply at 1.4 megapascals and 250 degrees Celsius down to 1.2 megapascals before it enters the turbine. And the exhaust of the turbine is at 10 kilopascals. If the turbine produces 110 kilowatts, Find the exhaust temperature and the quality if it is saturated. So, like other problems that we are solving, simulan natin sa mga bagay na nalalaman natin. Let's write down the given. According to the problem, your working fluid is steam. So, of course, that means that the thermodynamic tables that we are going to inspect later would be for steam. Also, the mass flow rate is equal to 0.25 kilograms per second. And if we are going to inspect our schematic diagram, meron lang tayong isang stream of mass. So, isang stream of mass na papasok sa ating throttling device, which is the same as the stream of mass na papalabas sa ating throttling device, na parehas lang din sa pumapasok at lumalabas sa ating turbine. So, clearly, the mass flow rate at state 1 is just equal to the mass flow rate at state 2, which is also equal to the mass flow rate at state 3, and all of them are equal to 0.25 kilograms per second. Now, sinabi rin sa ating problem na ang inlet ng ating throttling valve ay may pressure na 1.4 megapascals or basically 1,400 kilopascals. We converted it already this way dahil sa ating thermodynamic tables, ang mga pressures ay naka-kilopascals. Also, the temperature at the inlet of the throttling device is equal to 250 degrees Celsius. At the outlet of our throttling device, ang pressure niya ay 1.2 megapascals or basically we write it down as 1,200 kilopascals. And at the outlet of the turbine, we have a pressure that is equal to 10 kilopascals. So P3 is equal to 10 kPa. Also, the work output W dot T, or more accurately speaking, the power output in our turbine is equal to positive 110 kilowatts. So take note, it's positive because of the fact that it is done by the system. It is going out of our control volume. This problem can further be divided into two parts. The first one, magpo-focus tayo dun sa ating throttling device or dun sa throttle. So that means this control volume over here. So first, let us focus on our throttling device. If we read the problem carefully, wala namang special situation or special condition yung ating throttling device. Therefore, pwede nating sabihin na lahat ng default assumptions base sa ating formula derivation kanina ay tama. They are applicable in this problem, which means that the governing equation for our throttling device is HI is equal to HE. Now, recognizing that the inlet enthalpy is basically H1, and the outlet enthalpy is just H2 in our throttling device, masasabi natin ang final governing equation ng ating throttling device ay H1 is equal to H2. So, this is our first energy equation in this problem. Now, for the second part of this problem, iset up lang din natin ang ating energy equation. We have the turbine. Again, wala namang special assumption or special condition na binanggit sa ating problem. Therefore, we can say that all the assumptions that we said a while ago in our discussion will hold true, which also means that the governing equation is that W.CV is equal to the summation of M.I, HI, minus the summation of M.E, HE. Inspecting our turbine, makikita natin ang mass inflow natin dito ay M.2, whereas the enthalpy inflow is H2. And the mass outflow is M.3, and the enthalpy outflow is H3, or basically the enthalpy exiting your system. Sinabi rin natin na ang mass flow rate sa ating system ay iisa lang. Therefore, we can factor out the mass flow and say that that is just equal to M dot, and then we have H2 minus H1. Therefore, this is our second governing equation of this problem. Now, it's a matter of solving the states, and we are going to use our thermodynamic tables para makuha natin yung different state parameters. Now, let's begin with state 1. What do we know about state 1? Sinabi sa ating problem na ang pressure at the inlet of the throttling device is equal to 1.4 megapascals or 1,400 kilopascals. Also, the temperature is equal to 250 degrees Celsius. Let us inspect our thermodynamic tables for water. So, because we are using a steam turbine and steam is just water, punta tayo ngayon sa ating pressure entries. So, we have temperatures over here. Let's move downward. And tignan natin yung pressure entry levels. At 1,400, you can see over here that the saturation temperature is equal to 195.07. Now, how does that compare to the actual temperature of our inlet? We know that the inlet has a temperature of 250 degrees Celsius, and the actual temperature is definitely larger than your saturation temperature, which means that your working fluid at that particular state point is superheated vapor. So let me just write that down. T actual, which is 250 degrees Celsius, is greater than the saturation temperature at 1,400 kilopascals, which is equal to 195.07 degrees Celsius. Again, from here, we can deduce that our fluid is superheated vapor. Now, let us inspect our superheated tables. Punta tayo sa 1,200 kilopascals superheated vapor water over here. So, we have different pressure levels as you can see. We are interested in 1,400 kilopascals rather. Okay? So, at this pressure, 1,400 kilopascals and a temperature of 250 degrees Celsius, makikita natin na yung enthalpy ay equal lang sa 2,927.22 kilojoules per kilogram. So, isulat lang natin ang value na ito. We have H1 is equal to 2,927.22 kilojoules per kilogram. Now, let's move forward to state 2. Ano ba yung mga bagay na alam natin sa state 2? According to our problem, the pressure at state 2 or at the outlet of our throttling device is equal to 1,200 kilopascals. Therefore, P2 is equal to 1,200 kPa. Not only that, we also said in our energy equation over here that the enthalpy at state 2 is just equal to the enthalpy at state 1. Therefore, H2 is just 2,927.22 kilojoules per kilogram as we found it out a while ago. Okay? So now our state 2 is fully defined. Now let's proceed with the formula that we have derived a while ago for the turbine. As you can see here, we have m dot multiplied by H2 minus H3. Okay, so this should be H3. It is not equal to H1. Let us just correct it. So we have H3 over here and not H1. We already know the mass flow rate, that is just equal to 0.25 kilograms per second. We also know state 2 from the thermodynamic tables a while ago. And the power output W.CV is just equal to 110 kilowatts. So from here, masasolve natin ang enthalpy at state 3. Let us just plug in the numbers that we know. We have 110 kilowatts, or basically 110 kilojoules per second. And that is equal to 0.25 kilograms per second, multiplied by H2, which is 2,927.22, minus H3. Again, we have enthalpy at state 3 and not on state 1. Of course, we know that the enthalpy has units of kilojoules per kilogram. Okay, so plugging in these values in our calculator, we have 110. That is equal to 0.25 multiplied by the quantity of 2,927.22 minus H3, or let's say that is equal to X. Okay? And let us just use the shift solve function in our calculator. Let's input a relatively large number para mas mabilis siyang mag-iterate. Sabihin natin mga nasa 2,000, no? Just a random number. Therefore, we have an H3 value of 2,487.22 kilojoules per kilogram. So, let me just write that down. Now, we know the value of H3. So, bakit natin sinolve si H3? Dahil ito ay makakatulong sa pag-define ng ating final state. Whereas, the ones that we are looking for is the exhaust temperature, which is basically your T3, and the quality of your working fluid at the outlet of the turbine, X3, if it is saturated in the first place. Okay? So, ang ginawa natin dito ay sinolve natin ang value ng H3 Nang sa gayon ay ma-fully define natin ang state 3. So now we have P3 that is equal to 10 kilopascals and H3 is equal to 2,487.22 kilojoules per kilogram. We have two independent state parameters, therefore we can now fully define the state point. So writing that down on record, we have state 3, whereas P3 is equal to 10 kilopascals, and H3 is equal to 2,487.22 kilojoules per kilogram. Okay, we can inspect our thermodynamic tables and see kung saturated ba siya or superheated. We are currently in our superheated tables, so might as well go to 10 kilopascals over here. And makikita ninyo na at 10 kilopascals, the saturated vapor enthalpy, the one that you can see over here in SAT, it means saturated vapor, it's equal to 2,584.63. So, masasabi natin na yung saturated vapor enthalpy 2,585 almost is greater than the actual enthalpy, which is 2,487.22, yung nasolve natin kanina. So, punta tayo sa ating saturated tables para i-verify kung saturated mixture nga siya or hindi. We have 10 kilopascals over here. And as you can see, the value of your saturated liquid enthalpy is 191.81. And the value of your saturated vapor enthalpy is the one that we mentioned a while ago, 2,585 almost. And masasabi natin na yung actual enthalpy ay nasa pagitan nitong dalawa. Which means that the fluid at the outlet of our turbine is saturated mixture. Okay? So again, recall, kapag yung actual value ng ating enthalpy ay nasa pagitan ng HF at ng HG, we conclude that it is saturated mixture. Which also means that the exhaust temperature is equal to 45.81 degrees Celsius. So let us just write that down. To put it on record, we have 191.81 kilojoules per kilogram, which is your HF at state 3. This is less than the actual enthalpy, 2,487.22 kilojoules per kilogram. This is our H3, which is less than your saturated vapor enthalpy, 2,584.63 kilojoules per kilogram. That is Hg at 3. Therefore, to conclude, we have saturated mixture. So since it is a saturated mixture, the actual temperature at state 3 is just the saturation temperature at state 3, which is at 10 kilopascals, and therefore, as we have seen a while ago, we have 45.81 degrees Celsius. So this is now our T exhaust. Again, if you are confused kung saan natin nakuha yan, it is just in our thermodynamic tables. We have 10 kilopascals, the saturation temperature is 45.81 degrees Celsius, because we know that our fluid is saturated mixture. Now, since it is a saturated mixture, meron siyang quality that is between 0 and 1. To solve the quality, remember our formula. The actual value for enthalpy H3 is equal to the saturated liquid enthalpy HF at state 3 plus the quality at state 3 multiplied by HFG at state 3, whereas your HFG is your latent heat of vaporization that can be obtained from the table. So we have H3 that is equal to 2,487.22 kilojoules per kilogram equals 191.81 kilojoules per kilogram, which is just this one. Okay, plus X3 multiplied by HFG, which can be found in our table. That is just equal to 2,392.82. Let me just write that down. And finally, this is a one equation, one unknown scenario. So again, we can just use our calculator to solve this problem for us. We have 2,487.22 equals 191.81 plus x, which is our quality, multiplied by 2,392.82. Press shift and then solve. And again, para mabilis mag-iterate ang ating calculator, alam naman natin na yung value nito ay between 0 and 1, right? So let us just input 1. Okay? And we have a value of 0.9593 as the quality of our fluid at the outlet of your turbine. We have x3 is equal to 0.9593. So that is the problem for this session. I hope you learned something, and I encourage you to keep practicing, and I'll see you in the next videos.